Hello, my name is Ramya Raja, and this is my Lab 1 presentation. So in this lab, we are trying to track the constant acceleration of an object using different software and household items. We use the software tracker to gather exact measurements so that we can determine if an object is moving at constant velocity or not. So this lab is mainly used to exhibit Newton's second law, which states that force equals mass times acceleration, which we measure when the constant velocity of an object. I gathered data points from an object in motion to demonstrate the constant velocity of the object after it is set in motion. I conducted an experiment and created a computational model to compare it to. And then this is a video of my object in motion. So this is the tracker. This is a screenshot of the tracker software that I used. The software measures important values of an object in motion in a video. So first I recorded the object of a wiffle ball. I used a wiffle ball because it's round and circular and easy to measure in terms of constant acceleration. First I recorded the video of the wiffle ball in motion, then edited it to a time frame where the ball was at constant velocity. I then recorded the measurements of where the ball was at different 0.33 second intervals, or frames, for about 1.5 seconds. This is some of the data that I received. The initial position so in the tracker software they have you set an axis, and the initial position of the ball from the time that I started recording, this was the position of it with the axis that I set. The initial velocity is here where it's 0.52858 meters per second, which I calculated by taking a point, the one position of a ball, and subtracting it by a later position and then dividing it by the difference in time. Now I took the initial position right here and subtracted it by the position immediately after it, so it gave the most accurate initial velocity. And the whole observation period lasted only 1.47 seconds. Now, with the data that we collected, this was the position versus time graph. As you can see, since we were measuring constant velocity, it is fairly consistent. However, because it was an experiment, there are a few outlying factors that cause for this little bump here, or for the data to not be as consistent as a computational model. Speaking of, this is the computational model I constructed from code in the GlowScript software. Now, the GlowScript software was given the code for the GlowScript software was given to us, and we needed to edit certain variables and lines of code to match our experiment. So the edits that I made to the code was I had to change the mass of the system being the wiffle ball, because the mass was previously at 1, and using SI units it would be kilograms. Obviously the wiffle ball does not weigh 1 kilogram, so we had to change that. And then the time elapsed, because we had to change the time elapse to match our experiment, which was, our experiment ran for only less than 1.5 seconds. So to match that, we changed our time to less than 1.5 seconds. We changed the position vector and velocity vector to match the initial position and velocity vector, which we previously recorded in the experiment. And we needed to change the size of each timestamp to match the frames that the tracker software recorded, which was 0.33 seconds. So here's a comparison of our experimental data and computational model. The blue is the experimental data, and then red is the computational model. As you can see, the computational model is much more consistent in a straight line than the experimental data, and there is a big difference between them. Largely, I think the difference is because the wiffle ball was not a ball, it had holes in it, which could have caused a lot of different errors in construing the computational model that weren't considered while in the code. Okay. So here are a few questions that we had up for discussion. The orientation of the axis, which was the question was, how would it change if the orientation of the axis was changed? I actually did have to change the orientation of the axis, because when I was doing my recording, my camera was slightly sideways. So changing the orientation of axis to a couple of degrees lower than what it originally was construed actually helped my data significantly because I was able to have more accurate readings that read like it was going on a straight line. And in forms of zero net force, it's kind of possible to say how many pushes / pulls are acting on an object that resulted in having zero net force. We know there was an initial push, and then there was a number of forces acting on the object that were countering it, including gravity, kinetic friction, wind resistance, and more. And the combination of all of these is how we're able to construct that has zero net force acting on it. Thank you.